Thanks, Paco. So I'm Shivaram Venkataraman. I'm a PhD student in the AMPLAB at UC Berkeley, and I'm one of the major contributors to the SparkR project. And today I'm going to be talking a little bit about some of the stuff that we've done in the past, and also try and lay out some of the future directions that we're going to take SparkR towards. So I guess we've heard this a couple of times at this conference about the importance of R or the growing popularity of R, especially among the data scientists and people who are doing a lot of data analysis. Yesterday, Patrick, for example, showed a graph which showed how R's popularity has been growing over the past few years based on the Programming Language Ranking Index. And there are many reasons why R is popular, and primarily among them is that it contains a wide variety of tools that data scientists most commonly use in their workflows. This includes things like DataFrames that help you manipulate data very easily. There are also a large number of visualization tools that help you plot and observe different characteristics about your data set. And finally, I think the biggest strength for R is the wide variety of packages that have been written over the past decade or more that support a large number of functions that you would commonly encounter. There's a common thing in R that if you want to do something specific, you just need to search for the right package, and you'll mostly have a one-line function that you can run, which will exactly solve your problem. However, R has some limitations, and primarily among them is the limitation that it's restricted to a single thread and is restricted by the amount of memory available on a single machine. So trying to put together big data with R has always been a challenging problem, and there's been many different solutions in the past few years that have proposed different techniques to do this. Before I dive into what we actually do in SparkR or what we're actually going to do, I'm going to narrate a little bit about what I think are the predominant patterns that people do or people use when they're working with big data and R at the same time. So this comes from experience using R to do a number of projects, but also from conversations with other data scientists and looking at the workflows that people use today. What we've actually found is that it's not just one use case when you're using big data with R, but there are a number of use cases that people have in practice. So the names that I've given to these use cases are, the first one I call as big data small learning. Which is the case where you start with big data, but then you distill it down to a smaller problem. The second one is something that I call partition aggregate. And there are a couple of different varieties of this partition aggregate workflow, depending on the problems that you're solving. And finally, there's the use case of doing really large-scale machine learning. And I'll walk through these use cases in a little bit more detail, because that will give us a good idea of what do we need to have from a distributed system so that we can support big data processing from a high-level language like R. So to begin with, let's talk about this big data small learning problem. What do I mean when I say this? So the use case is something like this. You typically have a large amount of data that is present in a data store like HDFS or some Hive tables or something like that. This is usually, for example, in many organizations, created by some other team or for some other process. So there are click logs which are written out into a Hive table or something like that. Now, before you can apply a statistical learning model to this, what most users want to do is they want to do some amount of data cleaning, some amount of filtering to remove, let's say, duplicate rows or something, and some amount of aggregation, so that you probably want to aggregate all the clicks from a single user or things like that. And one thing that we commonly observe is that once you have done this cleaning, filtering, and aggregation, your data set actually reduces in size. Because the raw data you start with probably has a large number of fields, and you've selected some small subset of them that you'll actually be using for your machine learning algorithm. And so at the end of this cleaning and aggregation phase, what users typically do is they collect or take a subset of the data and bring it down to a single machine. And so in this case, once you have your data that fits on a single machine, you can then use all of the power of R to actually do your statistical computing. So then you can use the extensive set of libraries that you have to actually compute the model that's required on the specific data set that you have collected. So this is the big data small learning world where the input data or the source that we start with is really large. And so we need some tools and technologies to read in this input data to do this cleaning and aggregation. But the exact statistical analysis that we're doing is small and probably fits on a single machine. And from our conversations with people who use R, this is a common workflow that many of them observe today in their companies. But they do have problems in the first two phases here of reading an input and of also doing this cleaning aggregation stuff in a distributed fashion from the R language itself. The second use case, which comes up often at the end of the first workflow that I showed you, is you typically have collected your data to a small machine. Now you want to train a model using this. For those of you who were there in the ML pipelines talk yesterday, you might have realized that model training often involves actually a number of parameters, or tuning your model training process with a number of parameter values to figure out which parameter value works best for your case. This is often known as the parameter tuning problem, and if you have a number of parameters, let's say 4 or 5 parameters, each with 4 or 5 values, the number of different configurations you need to try actually multiplies as you add more and more parameters. So one of the most common use cases people have in this case is that they want to do this parameter tuning in parallel. So you want to run, for one value of parameter, you want to run your training process in parallel. And let's say your training process uses some specific R library, then you want to do something like this. You want to spawn off a number of parallel jobs, which will use your local R package to do the model training. And at the end, you want to aggregate the results from this in some fashion. And in parameter tuning, usually the aggregation people do is you pick the best model or the best parameters that fit very well for your data set. So this is an example of a partition aggregate workflow where the work is being partitioned from the driver to a number of machines, and it's then being aggregated at the end to figure out, to form the best model for the problem that we are solving. There's another small variant of this partition aggregate workflow, and this deals with how the partitioning happens at the beginning. And this is a case that we often see in applications like model averaging or boosting, where you want to train a number of models and sort of take in the aggregate value of all of them. So in such a use case, what people typically do is you again do some pre-processing on your data, but after you've done the pre-processing, you either use resampling or you use partitioning to create a large number of partitions from your data set, and then you want to train a model on each of these partitions that you've created. As similar to the previous workflow, there is an aggregation step at the end of it. And the aggregation step in this case could be combining the models together if you're doing something like model averaging. The last workflow that we see that doesn't fit the two workflows that I talked about before is the workflow associated with really large-scale machine learning. So this is a workflow that actually we've talked about a large number of times during this conference. And it goes something like you have a large amount of data. You'll use some featureization steps, which again need to operate on the entire data set. And this may actually even blow up your data set to create more features. And so you want to use a distributed machine learning algorithm in order to solve this problem. So this is a case that's actually tricky because all of your existing R packages, which work on a single machine, cannot be used out of the box in these settings because your data is distributed. And the fundamental reason for this is that when you implement a distributed machine learning algorithm, you have to be very conscious about how the computation and communication is spread out, and how do you write a scalable algorithm to get good convergence in reasonable amount of time. However, R still plays a role at the end of this where usually the model that you build itself is pretty small. So at the end of the training process, most users, what they want is they want the model to be inside their R process so that they can visualize some elements of the model or try to see if the model that they fit is good enough, use different metrics on these models, essentially. So just to summarize, the 3 different patterns that we see for doing big data analysis from R are to do big data small learning, where you have a large amount of data but a small statistical analysis problem, partition aggregate workflows, and also a large-scale machine learning. And so the goal of SparkR is to actually build a unified approach that lets us capture all of these workflows in the same system so that based on your problem, you don't need to go ahead and try to learn a new system in order to implement any of these things. So for the rest of the talk, what I'm going to do is I'm first going to give you a short history of the SparkR project and how it came about in the AMPLAB and what our goals were, et cetera. I'll talk a little bit about the existing release, Spark 1.4. This has already been covered in some of the keynotes and also in Chris's talk earlier this afternoon, so that'll be pretty brief. And at the end of it, I'll outline some of the steps that we're going to take in the future releases and what you can expect to see when you're here, say, next year. At the AMPLAB, as you all know, the Spark project was started there. And one of the main things that we spent a bunch of time thinking about is how do we put together a distributed computing engine like Spark with a high-level programming language, which is especially very popular in statistical communities like R. Our goals specifically were to combine the good properties of both of these systems. So Spark, as you all know, this audience probably doesn't need any introduction, is really fast, it's scalable, and it's also very flexible, letting you express a large number of algorithms and different operators on top of it. And R, as I've told you before, has its different strengths in terms of like the statistical analysis packages, DataFrames, and visualization, et cetera. So the initial effort that we did at the AMPLAB was to look at the Spark and specifically its RDD API and look at it as a parallel collection library. So what do I mean by that? So if you know the RDD API, you might be familiar that it contains a number of transformations, which are operations like map, filter, group by, reduce by key, et cetera, and a number of actions like where you can count on an RDD or collect an RDD, save it, and so on. So the first thing that we tried was to push the RDD class into R, or provide a handle to it from R, and mimic the API so that we could do the same things that you could do with an RDD in, like, say, Scala or Python. And so this was the R RDD that we created, and it contained all of the functions that you saw in the previous slide, and it contains some R-flavored versions of them. Like there was a function called lapply, which was similar to the map function in Scala, and it also included support for using existing packages using some new directives. So this was pretty cool, actually. So this was a prototype implementation that we did at Berkeley, and you could do interesting things like, for example, in this word count example, you could read a file from HDFS, which was itself pretty cool. And then you could also write functions which operated on these RDDs. And we had like closure capture that let you use some variables in R, and that they'll get automatically captured and shipped across machines, et cetera. And finally, you could also use inbuilt R functions. So in this reduce by key in this word count, you could also use like an inbuilt plus function in R in order to execute it. So we put this up on GitHub as a standalone project, and this was also a standalone R package that was not a part of Spark officially at that point. So you could install it on top of an existing Spark distribution, and we actually got a lot of feedback and interest from a number of users and developers who tried this out. After the step, what happened was a long period of open source development, where through the help of a large number of users and contributors, we made a number of improvements to the SparkR project itself. These improvements came in two forms. So the first are improvements related to the architecture of SparkR, which help improve performance, deployability, and other aspects of it. And the second class of improvements were related to usability. So the code that you saw on the previous slide, for example, had like 10 lines or 12 lines of R code that you need to write in order to just count the number of words in a file, which is a pretty complex thing to do. And so there are a number of improvements that we made to make it more usable. So I'll first talk about the architecture changes that we did. And to do that, I'll take a step back and try to explain the architecture of SparkR itself. So what happens is users who are using the system typically launch R from their desktops or laptops or wherever, and that launches the R process on their local machine. You could also use an R ID like RStudio, and the picture looks kind of similar to this. And when you do this, the SparkR package, you can load it as you would load any other package. And what that does is it creates a local JVM, and it connects to the JVM using this R-JVM bridge that we have. More specifically, the interesting part of the JVM is that we create a Spark context on the JVM, and there's a mirroring Spark context that we maintain on the R process as well. So using the Spark context, then you can describe any actions, transformations, and operations that you want to do. And once it's time to run these operations, we again use the JVM connection to sort of trigger these jobs that will run on the workers. Specifically, what happens on the worker side is that we have these executors, which are the Spark executors, which are JVMs running on these machines. And they, in turn, fork off R processes on the machines themselves and then run the tasks that you want to run or the R functions that you want to run. So one of the specific improvements that we made was in the design and implementation of this R-JVM bridge in order to make it easily extensible and in order to also help it to be deployable in settings like Yarn or any other like cluster manager that you might have. So to go into a little bit more detail, what does this R-JVM bridge do? The R-JVM bridge exposes a layer so that you can call JVM functions by using an R function that we have defined. So for example, if you have a static method called sum method in a class called RRDD, we have a high-level wrapper around it that lets you call this method directly from R and pass in any arguments that you want to pass into this method. So one of the cool things about this is that it automatically serializes the arguments that you pass in from R types into like the JVM types that match whatever function you're calling. And then the results from the JVM are also automatically serialized and brought back to the R process that is being executed. So one of the main requirements for doing this is that we needed like this to be supported across multiple platforms. So it needs to work on the R side and the JVM side, and also across different operating systems. So it needs to work on like a Linux or a Mac or a Windows machine and so on. So as a design choice, what we did is we used sockets in order to do this communication. And the socket libraries in all of these languages help us set up and run these things across multiple platforms pretty efficiently. Since most of this communication happens on a single machine, there's very little latency involved in this. And so this provides mostly a very, very interactive experience where you can create and use Spark context or create RDDs or DataFrames, et cetera. And they're also happening on the JVM, but it's happening really fast, so you don't see any effects of having this bridge in the middle. So this was some description of the architecture changes that we need to make. What about the usability side? So on the usability front, most of the feedback that we got from the users fell into one of these two buckets. The first bucket was that they needed APIs to read in data inputs from a large number of sources. The R users among you would know that CSV formats are, for example, really popular in R, and that there are a lot of functions that help you read in CSVs in the right form and like tabulate them, et cetera. But in addition to methods for reading in data, there was also a lot of demand for doing more high-level data manipulation. So if you looked at the RDD API, you needed to learn a lot of new constructs in order to do this. And for the average R user, they're used to a slightly different model. And the whole like key value pairs of like doing shuffles and reduce by keys are not very easy for a lot of users to pick up. So in response to both of these claims, we went ahead and designed and built the SparkR DataFrames. So this is the thing that you've been hearing about during the keynotes or the other talks that talk about SparkR. And the SparkR DataFrames actually address both of those concerns very elegantly, in my opinion. So at the very beginning, we have these data sources API, which Patrick and Matej talked about a little bit yesterday. And what they do is they solve the problem of trying to read an input into R from a distributed setting. Like I mentioned before, most of these users have like some data which is in HDFS or Hive tables, and they really just want to read in the data from R and start off the data processing from there. And using these data sources API, we're easily able to extend all of the data sources that you might be interested in. And because it's extensible through other packages, there are new ones for Avro or HBase and so on, which constantly keep coming up. The other thing that the DataFrames did is that they gave us support for schema. So when you read in an input file, for example, JSON, the column types are automatically inferred, and so you can use functions like average on like numeric columns in order to do your data processing. And finally, the DataFrame API was also built to mimic the local R DataFrame API, and also other like packages like dplyr, which are sort of state of the art for doing DataFrame work in R. And what this means is that it presents a very easy to use and familiar API for our users themselves. So the second half of the DataFrame, which actually informs some of the future directions for this project as well, is how do you split work between the R side and the Scala side? And so what we've done here is that the API and the high-level description of how the language or how the programming framework looks is all in R. But the main implementation of these operators and like different like join operations and stuff like that is actually residing in Scala. The nice advantages of this is that we suffer almost no performance loss from using a high-level language like R. And for most of these benchmarks, we get the same performance as you would get if you'd use Scala or Python as your primary language. So this support was, as you learned yesterday, released in Spark 1.4. And Chris Freeman gave this talk in the afternoon about an in-depth deep dive into SparkR DataFrames. And there's a link to the demo that he has on GitHub that if you haven't seen, you can try out, and you can play around with DataFrames using that. So now let's shift gears a little bit and talk about what's in the future of SparkR. And to do that, I'm going to return to the earlier slide that I had, which described these 3 big data processing scenarios and how our users have some of these common patterns that we see when we talk to our users. So to talk about the first one, big data, small learning, SparkR DataFrames are actually a great fit for this because they provide routines that help you read in input, perform filtering, aggregation, and most of the common operations that you would do before you apply your machine learning algorithm. However, the DataFrames in 1.4 was the initial release. There's a bunch of work that we're doing to improve it. Some of these include support for more column functions. So I showed you the average one on the previous slide. We're also adding support for more math functions and more string functions and transformations and so on. And also, we would like to add support for running your own R function on a particular cell in the data frame so that you can do your transformations on it. This is the UDF support that's present in Scala and Python data frames. So this is on the big data, small learning thing. And the final thing I'd like to mention about this is that this has a unique property where if you're not using any specific R transformations, then you really don't need the R process to run on the workers. So this is actually very easy for deployment as well, because all of the functionality is happening inside the JVM. You only need R running on the driver if you're using this particular pattern. For the other 2 patterns, there's work in progress that will help address some of the challenges in it. Specifically for partition aggregate, we're trying to come up with a simple parallel API for SparkR that let users express the patterns that I showed you before and build applications like parameter tuning or model averaging. A couple of the specific things that we'd like to address while building this are to integrate it very well with the existing data frames so that you don't pay any additional overhead or additional complexity in trying to read in specific data for doing like partition aggregate style workflows. And also, we would very strongly want to support existing R packages and add ability to ship R packages that you have installed on your machine to the workers and run them because a lot of these parameter tuning and model averaging workflows use like custom packages in order to do this. And finally, the thing that we want to do for large-scale machine learning is we want to exploit some of the features that are already present in Spark in the AMPLAB project and provide high-level features that are high-level hooks that let you call into these high-quality distributed implementations that are present in Spark. So here's a small example of what a very commonly used routine in Spark called GLM, which is for a generalized linear model. And we'd like to support such high-level operations for most common things like GLM, k-means, et cetera. Now, the key features are some of the extra things that we're doing in addition to what is present in AMPLAB is to be, again, able to use these data frames as inputs. So if you have your data source that you've read in from JSON or Parquet, you can directly feed it into these machine learning algorithms. And also, we'd like to support formulas, which are a very common method in R to express what are the variables and what are the labels that you're training your model on. So in this case, we are taking B and C as our features and trying to train it to A. And the last thing is, even though the machine learning is happening in a distributed fashion, I did talk earlier about how we want to bring the model down to a single machine. And a key part of that is to build a lot of summary statistics about the model so that users can evaluate the quality of their model. And so our users in this group might be familiar with the rich set of statistics that R provides when you type in something like summary of model. And we'd like to also support metrics similar to that in SparkR. The last thing that I'm actually very excited about is in making SparkR extensible. And at the beginning, I talked about how one of the main reasons for R being such a big success story is all of these packages that are created by our users, and there's a central repository where you can go and find these packages. So Spark already has an effort towards that called Spark Packages. And the one good news is that all of the existing, for example, data sources, they just work with SparkR. So for example, there's a CSV reader out there, and I used it to in one of these blog posts that I wrote. And you just need to pass in a flag, and there's nothing special you need to do when inside SparkR itself. But in addition to that, we want to actually foster this ecosystem of people who can write their own custom machine learning or other algorithms on top of SparkR. And so we're planning to add R package support and a bunch of example packages that will show users how they can write their own packages on top of SparkR. There's a big developer community that's grown around this project from the time when we were open source it from the AMPLAB to more recent times when it's been merged with the Apache project. A number of contributors from AMPLAB, Databricks, Alteryx, and Intel have contributed a lot of stuff to this project. For any of you who are R users or would like to play around or help out with the project, we'd always welcome more contributions in R. Or even if you know a bunch of Scala and you would like to help us build some of these things that I talked about, we'd be very interested in getting more contributors on board. So I'd like to conclude by summarizing my talk, which is that SparkR is an effort to unify a number of big data processing teams that we see from our users. In the Spark 1.4 release, we specifically have focused on DataFrames and helping users manipulate and filter data. And in the future, we plan to look at other models as well, including large-scale machine learning. With that, I'll take any questions. Thank you.
As compared with the Python API, what's the key difference besides the machine learning?
As compared with the Python API, what is the key difference? I think the Python API takes a slightly different standpoint in the design space, where the Python and the Scala API have like exactly one-to-one same functions that they try to maintain on both sides of it. So that's partly because like operations like tuples and key value chaining and all of these things are pretty natural in Python. So in SparkR, we are not actually trying to match all the APIs one-to-one at all. So we're trying to make it more friendly for the R users. And for example, some of the features like Chris showed this example earlier on about how you can delete a column in SparkR by just assigning null to a particular column name. That's a very R-specific feature that R users use in local data frames, and so we support it. But Python and the Scala API try to support what is more common for their users. So I think it's an evolving thing where we will support the same base functionality that you will be familiar with in like other languages, but it will be customized to make it feel more natural for our users. Yeah.
There is this open source project to port R to JVM called Engine. Have you played with that, and what's your experience?
Yeah, that's a good question. So there is an open source project which tries to re-implement R in the JVM. It's called Engine. So I haven't actually extensively used it. If I'm not wrong, it's still a work in progress where they're trying to support all of the R features. I think it's a pretty exciting project from a technical standpoint because it can probably allow us to do some more optimizations when we're calling from R to the JVM and then back into R and so on. And there are some contributors to the SparkR project who have tried it out. There was a talk at last Spark Summit East, which happened in March, which did some benchmarking using Engine versus like base R. You could probably check that out. Yeah.
Hi, I have a question. So what is actually the best way to help contributing with the new algorithm? Should we actually write them on Scala and then through the deployment it goes back to SparkR, or we actually build a normal R package like we do today, and then it becomes part of the product?
Yeah, that's a great question. So I think it depends on what kind of algorithm you're implementing. So like I mentioned before, if you're implementing a distributed machine learning algorithm, then the right approach is to put it into the Scala version, and then we'll build our bindings that let you call into the distributed version. Because fundamentally, the distributed runtime in Scala is way more optimized than anything that we'll do from the R side. But if you're building specific package, like if you're wrapping a bunch of existing R packages for things like parameter tuning or for doing these things, then you could write that on the R side. And that would be a useful addition because, for example, if somebody has some common format of data and you're going to read that in using DataFrames and then do a bunch of like existing operations on them, you can implement that on the R side. So I think the best way to do it is to open a Jira on like the Spark developer this thing, and then we can go over like exactly what algorithm is being implemented and see which side it fits in better. Yeah.
Great, thank you. We can take some additional questions also offline.
Yep. Okay.
Thank you very much.
Thanks, Michael.